All right, everyone, welcome to Wednesday's afternoon session. Our first talk of the afternoon session. We're very lucky to have Jared Speck from Vanderbilt University, who will be telling us about the mathematical theory of shock waves in multidimensional relativistic and non-relativistic compressible Euler. Jared, please.
Thank you for the invitation, Martin. It's been a real pleasure to hear the talks. They've been fantastic so far, in my opinion. I'm very thankful to the Black Hole Initiative for supporting this program, and I'm especially thankful to Martin for all the work he's put in. I think he's done a great job organizing and being responsive, so thank you. Okay, so this is a fluid talk, but it's motivated by considerations in general relativity for two reasons. First of all, a lot of the techniques and ideas come from mathematical relativity. And second of all, one of the big open problems is to extend what I'm going to talk about today to the coupled Einstein-Euler system and to understand shock waves without symmetry assumptions in that system. So that problem is open and very important. Okay, so most of what I'll say today is joint work with Leonardo Abbrescia, who is a NSF postdoc at Vanderbilt. And the talk concerns three papers. One is posted, one is almost posted, and one is a messy work in progress. And I'll say more about that during the talk. Okay, so what is the scope of the talk? Well, so nominally it's about 3D compressible Euler and the non-relativistic case, because this is where all the details have been written down, or most of the details. And a big consideration is that we allow for vorticity and entropy. So it turns out that these terms are very hard to deal with in some ways in the context of shock waves. In other ways, they end up being perturbative terms, but I'll say more about that later. Now, even though this is a non-relativistic 3D Euler talk in the large, there is a parallel theory that one can develop for the relativistic Euler equations, at least if you fix the space-time background. Let's say if you fix Minkowski space-time on R1 plus 3, or, oh, sorry, this should have been T2, R cross T2. Sort of the spatial topology is not particularly important for today's talk. And the discussion will focus on solutions that start off smooth. So the initial data are going to have a lot of regularity. I won't say exactly what it is, but for technical reasons, it's got roughly 20 derivatives worth of Sobolev regularity. And these initially smooth solutions, they end up forming a shock. And the purpose of this talk is to sort of show you in full detail what the singular surface looks like. And for the regime of initial data and solutions that I'm going to consider, they will be perturbations of plane symmetric solutions. And so there's not going to be any dispersion, because in 1+1 dimensions, Euler is basically a transport system, and there's no powers of T or R that enter into the analysis. There's no decay. And so that makes a lot of the analysis easier, because you don't have to worry about powers of T and R. You can just focus on the singularity. And for this reason, a lot of what I'll say should carry over to the coupling, or not coupling, but the relativistic Euler equations in an arbitrary Lorentzian spacetime where the Lorentz metric is prescribed. So basically, if you have a sufficiently smooth Lorentz manifold and you put the relativistic Euler equations on that manifold, you should expect that you can prove large data shock formation using the kinds of ideas that I'm going to talk about today. And again, most of the talk will focus on plane symmetric solutions. However, the techniques certainly can be applied to other solution regimes, such as small, compact perturbations of non-trivial fluid solutions, non-trivial constant state fluid solutions. Okay, so this picture has pretty much the whole story in it. And some of this picture is an open problem. So that's this hypersurface K that I'm going to talk about in a little bit. And part of this picture, which is concerns this piece called B. So this is what's called the singular boundary. That's going to be my main focus of this lecture, is the singular surface B. And so this is the paper that's almost completed, concerns this surface B. And the future work concerns this other surface C, or C bar, I should say. So this ends up being a null hypersurface, and it plays the role of a Cauchy horizon in fluid mechanics. Okay, so let me start to digest this picture, and it's going to take me a long time to talk you through this because there's a lot going on. Okay, so down here, sigma 0, this is a flat, if you want, Cartesian slice where very smooth initial data live. And then the evolution takes place up here in this region. And you should think that I'm studying perturbations of plane symmetric solutions, where the planes, exact plane symmetry corresponds to the t and x1 directions. And my perturbations away from symmetry are the x2, x3 directions. Obviously, I have to suppress one direction here. And these variables live on the two torus. But the topology is totally irrelevant for most of what I'm going to say, because by finite speed of propagation, you can sort of reduce the study of your favorite manifold to something that looks like this, at least locally, at least for certain kinds of initial data. Okay, so let me tell you what happens in the dynamics for the solutions that we study. So I should say that we study open sets of solution. The solutions are approximately symmetric, but they don't have exact symmetry. Okay, so ignore for now this hypersurface called K. That will enter into the story later, but not in my work. This hypersurface enters into the story if you want to study weak solutions, which is something other people, including Christodoulou, have done. Okay, so ignore K. So here's what happens. That you need to know the punchline to sort of even get started understanding what's going on in the problem. As the solution evolves, a first singularity forms. Now, as it turns out, the proper point of view in fluid mechanics of what is a first singularity is not a point. It is a codimension 2 submanifold. And so it's labeled a partial minus B here. So B is a 3-dimensional manifold with a boundary, and the pass boundary is what I'm calling partial minus B. So B is 3-dimensional and its pass boundary is 2-dimensional. So for reasons that I'll explain, you should think that this is the first singularity, and it ends up having the character of a space-like surface embedded in the Cartesian space-time. Or if you're working with the relativistic Euler equations, you should think that this is a picture in Minkowski space-time. So equipped with the standard rectangular coordinates differential structure. Okay. So a first singularity forms. It's this codimension 2 submanifold, and then the solution continues to evolve, and more points become singular. And if you union together all the singular points, you get this singular surface B. And this is called the singular boundary. And what actually ends up happening on this singular boundary is that certain first derivatives of the velocity and density blow up. Certain first derivatives. In fact, you can say precisely what blows up and what doesn't. What blows up are derivatives in directions transversal to characteristics, and the characteristics are not shown on this picture. They're shown on a different picture. Whereas derivatives in directions tangent to the surface, to the characteristics, remain bounded. However, the fluid variables themselves do not blow up. They remain bounded. It's only their first transversal derivatives that blow up. Okay, and what will eventually happen in the third paper is that along the Cauchy horizon, you do not see any singularity whatsoever. So basically, if you start seeing infinity down here, you'll stay infinity all the way up to the Cauchy horizon, except the Cauchy horizon does emanate from what I call this first singularity. Sometimes we also call it the crease because of the character of the picture. The Cauchy horizon also emanates from the crease, and there is a singularity along the crease. That's where the first singularity is. But away from the crease, there's no singularity along the Cauchy horizon. And as it turns out, at least sort of locally, you can say that the maximal development of the initial data coming from the portion of the initial data down here is the solution region in between sigma 0 and the Cauchy horizon, and all the way up to B. So K plays no role in this discussion at the moment. So this is this is what you might call a description of the maximal classical development. So this is basically the largest possible space-time classical solution and region that is uniquely determined by the initial data down here. Now, I should warn that to prove true uniqueness of the maximal development, you sort of need to know the global structure of the solution. There's a beautiful paper by Relied and Eperon and Spersky that shows you that there can be non-uniqueness of maximal developments for seemingly reasonable equations. So to prove some kind of global uniqueness of maximal development type result, one thing you can do is to actually construct the maximal development. And then basically the ideas from that paper can allow you to show that it's unique. And here we're doing things locally. So this is not giving you the global structure. So one would need to work harder to say something about global uniqueness of the maximal development. Okay, so again, still forgetting about K. It's very hard to do estimates up to the Cauchy horizon, and it's very hard to do estimates up to the singular boundary. Why? Multiple reasons. First of all, stuff is blowing up along the singular boundary. So when you're proving PDE estimates, you have singular terms all over the place, and you need a paradigm to control them. And in the irrotational case, when the vorticity and entropy are zero, that paradigm was given to us by Christodoulou. Okay, and it turns out that that paradigm can be extended to handle the presence of vorticity and entropy. And the real work on that extension began with my work with Jonathan Luke. And so this is a continuation of the program that was begun with Jonathan about, oh God, Jonathan, we're getting old, 6 years ago now. Okay, so this problem is degenerate because of the blow up. And moreover, this surface B, as it turns out, is ruled by integral curves of a vector field L. So this is the Cartesian picture, a vector field L, which from the correct true geometry of the fluid problem ends up being a null vector field. So there's a sense in which this singular boundary can be thought of as null. Okay. Now it's actually very difficult to make full sense of the causal character of the singular boundary because there's some degeneracies that occur along here. So this statement should be sort of understood with a grain of salt. It's the point is to sort of give you the idea that you're going to have to derive estimates up to a hypersurface that is kind of behaving like a null hypersurface. And as we all know, in the study of wave equations, you lose control over certain derivatives, the transversal derivatives, when you're trying to do PDE estimates up to null hypersurfaces. So this makes the analysis difficult just from the point of view of wave equations. Furthermore, as it turns out, you cannot close the problem, at least the only way we know how to think about it. You cannot close the top order estimates for the vorticity and entropy using only hyperbolic estimates. There is an elliptic type setup that one has to use to avoid the loss of the derivative in the estimates. And so that means you have to do elliptic estimates on domains that are adapted to the shape of the singular boundary, which by the way is not known in advance. So you have to do elliptic estimates for these quantities to control them, and the boundary is not known in advance. And not only that, but the boundary itself, the surface B, has no sort of natural nice description in terms of the Cartesian or rectangular differential structure. That means the elliptic estimates, you really have to work hard to do div curl estimates on surfaces that are bounded by regions that look like this. Okay, so so that's the statement about, you know, what makes the problem hard and what are we actually studying. Now, what about this hypersurface K? So this is the open problem. K will eventually, hopefully when Christodoulou releases the next mammoth monograph from the sky, K will be what is called the shock hypersurface. Okay, what is this? So it turns out that if you want to study the flow past the first singularity, and again, first singularity means this codimension 2 crease right here, and you impose the weak formulation, Okay, then in the classical region where nothing is blowing up, the weak formulation and the standard PDE formulation completely agree with each other. But as soon as you have a first singularity, there is a new speed of propagation that is introduced by the weak formulation, which is not present in the classical formulation. That is the speed of the shock hypersurface itself, which, as it turns out, is supersonic in this region, and it juts out into the maximal, what you might think of as the maximal classical development. Okay. And what is the shock hypersurface K? Well, after somebody solves the shock development problem with vorticity and entropy, the full problem, K will be a hypersurface across which the velocity and density jump. Okay, there's jump conditions that one imposes. They're the usual jump conditions, and they will jump across this shock hypersurface, and then the expectation is that the solution will be essentially C infinity on either side of the shock hypersurface, and we'll just experience a jump. Now, the actual nature of the jump is very tensorial in nature. I don't mean to, give a precise description of exactly what jumps and what doesn't. It's just to give you the idea that if you impose the weak formulation, there is a new speed of propagation, the shock hypersurface, and you won't see that if you study the maximal classical development. In particular, the portion of this picture that lives in between K and B is irrelevant from the point of view of the shock development, studying the weak solution. So the classical solution that I'm studying today that lives in between K and B in this narrow wedge is not part of the weak solution. So you might ask, well, why do I construct this maximal classical development if it's not going to be part of the weak solution at the end of the day? So two reasons. First is simply an interesting math problem that this same problem exists for other hyperbolic PDEs, and it's just a general question of interest to study the maximal classical development. Second answer, the known approach of constructing K in what's called the restricted shock development problem. Okay, so let me back up for 1 second. What is restricted shock development problem? Restricted shock development problem was solved by Christodoulou. It's basically the problem of solving uniquely, weakly past the first singularity when you ignore vorticity and when you ignore entropy. So you ignore those variables. The laws of thermodynamics and the jump conditions tell you that even if you start off with an isentropic solution with zero vorticity, then after the first singularity forms, and you solve the solution weakly, the vorticity and entropy are going to jump across the shock hypersurface. So they cannot possibly, even if they start off zero after you solve the weak solution, they will not remain zero, they must jump. And in his important monograph from 2019, Christodoulou ignored the jump in entropy and vorticity and produced a weak solution to a different PDE system. It's basically what you get when you take Euler and you ignore the jump in entropy and vorticity. And he produced a weak solution up here in the region that lives, well, let me not exactly say what region, but it lives to the future of the singularity. Now, what were the initial data for the shock development problem? Okay, so he started from essentially this picture. So in the restricted shock development problem that he solved, he basically started from assuming that you have a Cauchy horizon, assuming that you have a crease, and assuming that you have constructed the singular boundary in the irrotational case. And he used the full information about the singular boundary B as a barrier, as a mathematical barrier, and in his iterative solution to the restricted shock development problem. So basically, he actually used the full information about what goes on the singular boundary to construct K. Another reason you might care about the classical picture, even though you might want to even though you might mostly be interested in the weak solution at the end of the day, another reason you might care is that K actually emanates from the crease. So it really pops out of the same codimension 2 submanifold. And furthermore, it starts off tangent to the singular boundary, right? So asymptotically, K and B can be kind of thought of as being the same. And so you should think that by deriving this picture, it's basically setting up the full shock development problem the right way, thereby sort of guaranteeing you that you have initial data that you're allowed to study that come from initially smooth initial data. Okay, so that's all I want to say about this picture for now. Okay, so let me zoom in on the singular boundary and at least show you the collapse of the characteristics. So I didn't formally define what is a characteristic, and if I have time, I'll give formal definitions later in the talk. Here, I mainly want to show you that what's going on in the singularity formation is just some higher dimensional analog of what you see in burgers. So what we have down here are a family of characteristic hypersurfaces. There are 3 shown in this picture. Before the singularity forms, they're sort of supposed to look equally separated, and then they come together up here on the singular boundary B, and their density goes to infinity. Now, there's something very important about this collapse that I want to emphasize for this particular problem that I solved with Leo, but also for the shock development problem. So it turns out that in the regime that we're studying, which is basically the only regime we can hope to understand at the moment based on the techniques that we have, even though the density of these characteristics becomes infinite up here, they never actually intersect. So if you want the map from this characteristic down here to its image up here on the singular boundary, that's an injective map. And it turns out that injectivity plays a really important role in setting up the shock development problem in the way that Christodoulou did. If you don't have this injectivity, then basically I wouldn't know what to do. And in one space dimension, you can actually construct solutions where the injectivity fails. Okay, so really this is an assumption about the regime one is in, and it happens to be what there's a sense in which you may think of it as the generic regime. I'll try to say more about that later if there's time, but you should at least know that there are solutions which are possibly unstable in some sense that live outside of the regime that I'm addressing today. And it actually turns out that to solve the problem, you really need to quantitatively understand the degeneracy that happens. And it's very directionally dependent. In the worst possible direction, the degeneracy of how these characteristics fold into each other, it can be thought of as being the same as the degeneracy of the map U goes to U cubed at the origin in some directions, whereas actually on the singular boundary, it's more of like a quadratic type degeneracy, like more like a U goes to U squared at the origin. But those details don't really matter for the purposes of this talk. For the PDE, again, for the PDE analysis, they actually do seem to matter a lot. Okay. So I've talked a lot about that picture and what happens before the shock. Let me say a little bit about what goes on after the shock, even though that's not something that I've worked on. I just want to highlight that there's been a lot of fantastic progress. So in 3 space dimensions in spherical symmetry, Christodoulou and Lizebach solved the restricted shock development problem. So they produced a local solution that's weak, starting from the maximal classical development, if you want. So they solve past the singularity weakly for short times. And it should be understood that the weak solution produced through this procedure is unique within the class of solutions that satisfy certain estimates. So my understanding is that you can't really, to this day, make sort of a global uniqueness claim, but rather uniqueness within the class of solutions that satisfy certain estimates. Okay. And then this is the 2019 monograph of Christodoulou that I mentioned earlier, his solution of the restricted shock development problem in which the vorticity and entropy were ignored. And he did this in n space dimensions for the non-relativistic compressible Euler equations and also for the relativistic Euler equations. Then there's been progress in which vorticity is present. So there's this interesting approach by, it started with an approach from Buckmaster, Scholar, and Wickel to understand what I would call non-degenerate, fully non-degenerate shock formation. So later in the talk, I'll explain exactly what I mean by that. So they had some papers on the formation of the shock. And then with Drievis, under the assumption of azimuthal symmetry in 2D, which is the symmetry class in which vorticity is allowed to be non-zero, they produced a local and time unique weak solution past the first singularity. So they solved the shock development problem with some vorticity in a symmetry class for short times. So that paper was from last summer, to give you a sense of the timing. So let me back up several decades and mention Maida's work on local and time weak solutions. So I want to highlight what's different between what Maida did and what is the shock development problem. So Maida started from initial conditions that contain shocks, basically. His initial data had a jump in it, and importantly, his initial data were allowed to have vorticity and entropy. And what he produced was a local and time weak solution to the Euler equations in weak form, obviously. Again, I want to stress that the difference between the shock development problem and what Maida did was in the shock development problem, you're actually studying the transition of the solution from being classical to weak. Like you're trying to go from C infinity to first singularity to weak solution. And the shock development part of that program is starting from the first singularity and then progressing to the weak solution. So it's really about describing the transition. And as it turns out, that is a very challenging problem, and it seems to be a lot harder than starting from initial conditions that already have a jump in them. So it's harder, but I should say that this work is considered a breakthrough. I think it's still considered a breakthrough, and Maida won several awards for this. So it's still a big deal. I also want to point out that Dan Ginsberg and Igor Radnyansky have a great new result. So this concerns basically what you can think of as quasi-linear wave equations, which are what you encounter in the context of the restricted shock development problem. They studied perturbations of spherically symmetric global and time weak solutions, and they proved, for if you want open sets of initial data, that the perturbations, which do not have to have exact symmetry, even though the things they perturbed were spherically symmetric, the perturbations were allowed to be general. The perturbed solution to the weak problem exists globally. So that's the first global existence result to a weak solution without symmetry assumptions. So that's a great result, and it's clear that the ideas they introduced could be useful in other contexts. Besides the model problem that they looked at. Okay, and then I want to highlight that there's other things one can do in the context of weak solutions. There's been some really interesting progress by Lisebach recently. He posted 2 papers within the last few weeks on 1D barotropic flow. So barotropic means that there's no entropy, and the pressure is just a function of density. He studied the interaction of shocks in 1D. So you have one shock wave here and another here, and they're colliding, and he solved for a weak solution to a small neighborhood of the future of their intersection. Okay, and then another paper that he produced is on the shock reflection problem, and this is the PDE problem where you have a boundary. Physically, you might think of it as a wall, and the shock bounces off the wall, and you want to understand the weak solution in a neighborhood of that interaction, and he did that as well. And so how does this fit into the multi-dimensional program? So the basic idea of what I'm doing with Leo and what other people are doing is we're trying to build up techniques that sort of treat individual regions and individual kind of interactions one piece at a time, in the hopes that one day somebody will be able to use these individual components to sort of establish a more global picture of the behavior of the fluid. And here, global could mean global in space, or I mean, global in time seems really hard, just because of having to control the vorticity. Well, at least, okay, maybe something, maybe one day in 2D something could be done, because in the incompressible case, in 2 space dimensions, for Euler, incompressible, you have global existence. So, maybe one day someone could say something in some regime in 2D. But again, the basic idea is we're trying to develop building blocks so that we can understand different regions of the fluid and different kinds of interactions towards a more global theory. Okay, so we're at the very beginning of this program and we're just working on the different building blocks. Okay, so now I want to talk a little bit about the analysis that I use with Leo to construct the maximal classical development. And I'm going to shy away from the PDE estimates, which are extremely technical, and I'm going to sort of focus on the geometric setup, which I think is more memorable and maybe even more interesting for you to hear about. Okay, so the way we understand the flow is through the interaction of through 3 coordinate systems. So the first is the standard Cartesian coordinates. So Cartesian, that's the proper language if you're talking about non-relativistic flow. If you're talking about relativistic Euler, then you should think that these are rectangular coordinates on Minkowski spacetime. Okay. The second coordinate system that we use, we call geometric coordinates. This is basically the same as what, not so different than what Christodoulou used in his earlier works on shock formation, and it's exactly the same as what I use with Jonathan in our joint works on shock formation. These are geometric coordinates where all you do is you replace x1 with a solution to the iconal equation, the solution capital U to the iconal equation, where this metric G, so this is a Lorentz metric called the acoustical metric, and this has very little to do with the space-time metric. So this is the metric that governs the propagation of sound waves, and this is the metric that you can think of as describing the true geometry of the fluid. And I'll show you later on in the talk exactly what this looks like. Okay, so this is the solution U to the iconal equation. So this is how you construct the characteristics. Just as in mathematical relativity, the level sets of U are characteristics, which you may think of as sound cones, except topologically in the regime we're looking at, they're more like sound planes because of the approximate plane symmetry. Okay, so this coordinate system basically unfolds the characteristics and sort of removes the intersection and kind of secretly tries to hide the singularity formation. And you can basically make the solution look extremely smooth in this coordinate system with one caveat. When you go to do energy estimates in this coordinate system, at the very high orders, you see some remnants of the singularity. You see some really degenerate behavior of the top order energies. And that makes the energy estimates incredibly difficult to close. However, that part of the problem has essentially been understood since Christodoulou and since my work with Jonathan. the singular strength of these energy estimates at the very high orders. Now, the new ingredient with Leo is basically a new time function. So instead of using the background t, we have a new time function called tau. And as it turns out, at least the way we approach the problem, you don't need just one new time function, you need a continuum of them. So for kappa belonging to a small interval 0 to kappa naught, we construct, for each such kappa, we construct the new time function. And this time function is when you use it to foliate space-time, it terminates in one piece of the singular boundary B. Okay, it allows you to see one portion of the singular boundary B. And in my next slide, I'll show you exactly what's going on. Now, one good thing about this, about working in this field is that you sort of know what you want the singular boundary to be. And it ends up being a portion of a level set of a function called mu that looks rather smooth in the geometric coordinates. And so this is called, in the shock literature, this is called the inverse foliation density. So mu equals 0 means the characteristic density has gone to infinity and the characteristics have piled up. In the relativity literature, you see this called the null lapse sometimes, this mu. And the word proportion here is important. It turns out that this level set, there's a sense in which part of it, you want to think of it as inaccessible, because that part sort of wants to have a time-like character. And so you can't hope to access that time-like portion in the context of the maximal development. So I'll say more about that on a later slide, exactly what's going on the portion of mu equals 0 that actually belongs to the maximal classical development. Okay, so how do you construct this these tau k? Well, they solve a transport equation. So for each, tau kappa, they solve a transport equation. For each kappa, there's a vector field called W kappa that we construct. And then we just, you need initial data for tau kappa. And we then once you have the initial data, you transport it. Now, what are the initial data for tau kappa? Well, it's very convenient to choose them to be minus mu on a certain hypersurface. So in the regime under the way the setup works is that before the singularity, tau is negative, and then tau equals 0 corresponds to being exactly on the singular boundary, exactly where the blow up occurs. Now, where do the initial data live? I'll show you in the next picture. They live on what we call a rough geometric hypersurface. So the initial data for this time function are prescribed on a hypersurface that ends up being a level set of some derivative of mu being set equal to a constant. And then I think it's just better to jump right to the picture and sort of explain to you what's going on. Okay, so here's an example of two families of these foliations. The first the left picture right here. So this is with kappa equals 0, and this is the setup uses to detect the crease. This again the first singularity, the past boundary of the singular boundary, and the second picture is with kappa positive, and it allows you to detect a different portion of the singular boundary that lives to the future of the crease. Okay, so let me say more about these pictures. Okay, so this hypersurface that runs kind of vertically in this picture, that is where the initial data for the rough time function tau 0 are given. And in the picture, this is called x sub 0. And again, this is actually a level set of a transversal derivative of the null lapse. So that's the surface where you initialize the data. And then this vector field W0 is set up, cooked up so that you basically, maybe it's better to talk about this picture. This vector field W is cooked up so that when you flow, you never crack, you flow just a little bit underneath the singular boundary. So this vector field W is tangent to the level sets of the time function, and it's cooked up so that you always flow underneath the singular boundary. And in order for this picture to be valid, and in order for this setup to work, this is where we're using an assumption on the initial data that guarantees that you have some kind of some kind of convexity of the singular boundary in the x1 direction. So this is something that we call transversal convexity. So basically, you need to know something about some weak form of convexity about the singular boundary in the x1 direction in order to cook up this picture. Okay, so these are the initial data surfaces for the rough time function. And then along this surface, we choose the initial data for the rough time function to be minus the null lapse. Okay, and so it turns out that the intersection of a level set of the null lapse and this hypersurface gives you these codimension 2 tori that are called t sub minus tau 0, and then up top you have t00, which ends up agreeing with the crease. So I guess a key point to take away from this part of the construction is that these codimension 2 surfaces, these tori, topologically tori in this picture and this picture, they play a fundamental role in this problem, and that's a theme that we've seen echoed over and over in different problems in geometric analysis discussed in this program. The important role of finding good codimension 2 hypersurfaces. Okay, so let me tell you a little bit about the framework for the PDE analysis. So there's a really boring part of the flow, which is basically start in between sigma 0 and before you get really close to the singularity. What goes on here is very boring. This is basically standard Cauchy stability if you're studying perturbations of plane symmetry. nothing interesting happens. Similarly, here in this region, nothing interesting happens. So basically, in this region, you just use Cauchy stability to say that the data on sigma 0 induce some initial data on this initial hypersurface down here, and similarly, the initial data on sigma 0 induce initial data on this hypersurface down here. And then the goal is to switch to a more fancy machinery once you have once the solution is in this state, and you follow the solution all the way up until tau equals 0. So this is like down here, tau is some negative value, and then up here, right when you first touch the singular boundary, tau becomes 0. And this setup is cooked up exactly so that when tau becomes 0, you become tangent to the singular boundary in exactly a codimension 2 submanifold. So in this picture, it becomes tangent to the singular boundary exactly at the crease. Okay, so basically from the PDE point of view, you want to start with initial data here, and then you kind of want to ground wall all the way up until tau becomes 0, and then voila, the crease is sitting inside of your top surface. And similarly, down here, you start with smooth initial data here, and then ground wall all the way up until this time function equals 0, and then you get this piece right here. And so this is cooked up so that the singular boundary is the union of all of these tori, one for each kappa. So this is the crease is the kappa equals 0 torus, and then here is this purple line here is supposed to be the torus within the singular boundary that is generated by a positive kappa. Okay.
Jared.
Yes.
Sorry, I apologize.
Yeah.
I don't quite understand the fact that you have these many pictures. So
okay,
in other words, you have different time functions. Why do you need that?
Okay. Because so you might say, why do you do that? So you might say the natural thing to do, you want to touch the singular boundary. Why don't you use these as why don't you use these level sets of the null laps? Why don't you use them as hypersurfaces? That would be a reasonable question. Why don't you try to do it all in one go?
Yes, right.
The answer is that if you do that, part of these hypersurfaces end up being time-like, and you cannot do energy estimates along them. That is a very good question. So you need to do estimates across a large portion of space, and as it turns out, only a portion of the level sets of the null laps are space-like, and the other portion ends up being time-like, so you don't get PDE estimates on them. So this is like a truncated approach to, we have to remove the portions of the level sets of the null laps that fail to be space-like.
Okay, so that's what is you are looking only at space-like regions, and you do this.
You only have access. Yeah, you can't possibly get access. You can't do estimates on the time-like regions. That's exactly what's going on. That was a very good question.
So you isolate the time-like regions, and that's why you get.
Yeah, we remove them. Yeah, we cut them out, and so these hypersurfaces are all space-like.
And everything is initialized at initial data, so you are starting from initial data with.
Really, you could say the real data are down here, sigma 0, but then these data induce. You have to construct this first. You have to construct these first. You have to construct these first sigma taus, or these sigma tilde taus. That's part of the construction. In the beginning, there's, and in fact, the structures that you need to construct these time functions, they don't appear until late in the evolution. So basically, you can't even draw this picture down here near sigma 0 necessarily. It's only very late in the evolution when the character of the singular boundary really starts to show itself that you can start this construction. So if you want, you really do kind of need two gauges, like what goes on down here, and then once you get close to the singularity, then you can start constructing these things. Okay. And of course, I said it, you have to do sort of hyperbolic energy estimates for the wave part of the system. And then there's these elliptic estimates that you also have to do on these regions to handle the vorticity and entropy. And that's what makes the elliptic estimates are really what make the work so technical.
I still don't understand what is the role of this hypersurfaces, these time-like hypersurfaces.
So
They're used as boundaries.
these provide the initial data. You need to say the initial data for the for the time functions. Okay, I want the initial data to be minus the null lapse. But where do the initial data live? You have to put them on a hypersurface, and I want a whole family. I want to foliate space-time with these sigma tilde tau. And I do it by solving a transport problem. So each sigma tilde tau is constructed by flowing along a W, starting from where?
No, this I understand, but what is the role in the hyperbolic estimates? What role do they play in the hyperbolic estimates?
So maybe I can jump way ahead to the picture that sort of shows you what's going on. So the portion of the singular boundary that you can hope to access is the intersection of the level set mu equals 0. So this is where the null lapse vanishes, with a set where some transversal derivative called x in this formula, the x derivative of mu is strictly negative. So that's exactly so it's the intersection of these two things that you can hope to, if you want, this is the part that you may think of as space-like in some sense. And then the level sets of x mu, where the negative level sets, so x mu, I'm sorry? The negative level sets of x mu are exactly these, what I showed in this picture. So x sub 0 is the level set x mu equals 0, and x sub minus kappa is the level set x mu equals minus kappa. So if you want, these sort of give you these help you find the correct region where you know that these surfaces are going to be space-like. This is, it's exactly these surfaces that you use to ensure that the time functions are in fact space, or their level sets are space-like. Okay. Did that help, Sergio? Okay. So sort of to reiterate, the strategy is to decompose the singular boundary into these topological tori. Each torus, as it turns out, ends up being 2 degrees less differentiable than the fluid. So these can be thought of as rough hypersurfaces. These are provably 2 degrees less differentiable. So this tells you that even though the basic scaffolding, the region on which you need to do estimates, is rough, you're going to have to find a different mechanism to sort of for the regularity theory of the equations, and that's where the geometric coordinates come into play. You can't when you're constructing differential operators for the problem, you can't use this picture directly, because then you'll lose derivatives. So you need yet another differential structure for the basic regularity of the problem, and that's where you use the Icoma function, just like in other works on shock formation. Okay, so let me talk a little bit about previous results on understanding some portion of the boundary of the maximal development. So this already started in the 80s with work of Fritz John, who for strictly hyperbolic systems in 1+1 dimensions, he at least understood what goes on at the time of first blow-up. So here time should be understood as flat Cartesian time. So he followed the solution up until the first Cartesian time of blow-up. And there have been a lot of recent works in 1+1 dimensions sharpening what Fritz John did. So you can look at Christodoulou Perez and An, Chen, and Yin have been doing similar things for the equations of elasticity. These more recent works go beyond what John did, and they're more in the style of the pictures I'm drawing today. Again, these are in 1+1 dimensions. A real major breakthrough came in the late 90s by Alinak when he studied quasi-linear wave equations, and he studied initial data that have a unique lowest blow-up point. And I'll show you exactly what I mean on the previous slide. Or sorry, on the next slide. I'll show you a picture of what I mean by lowest blow-up point, and that should be thought of as an assumption on the regime under consideration. It does not cover, this regime does not cover perturbations of plane symmetry. Then another huge breakthrough was Christodoulou's famous monograph from 2007, which concerned the irrotational case for relativistic Euler. And so in the last chapter of his book, he took his PDE estimates and he sort of unioned them together and described implicitly some portion of the maximal development. And if you take a close look at what was done, the portion that his book yields access to is a portion that is accessible using Cartesian flat time functions. So instead of using foliations that were exactly adapted to the structure of the singular boundary, he was just using flat hypersurfaces. And if your singular boundary has convexity, then you can probably get the whole singular boundary using this approach. But in regions where you don't have full convexity, you're going to be missing part of the maximal development through this approach. And then following Christodoulou, there was lots of work by various people on wave equations, extending Christodoulou's result to other regimes. I did work with Gustav and Jonathan and Willy Wong, and then there's work by Miao and Yu separately and also together. Like all of this is on wave equations. With Jonathan, we took Christodoulou's framework for approximately plane symmetric initial conditions like today, and we added vorticity to the problem. First in 2 space dimensions, and then later, much more recently in 3D, we added entropy. And we followed the solution to the time of first blow-up and gave a full description of the singular set at the Cartesian time of first blow-up. And then there's the other approach by Buckmaster, Scholar, and Vikol based on self-similarity and modulation parameters. So this is a philosophically very different approach. It's much shorter in the regime where it works, and it allows you to follow the solution to the when there's a unique lowest blow-up point, you can follow the solution up until the time of first blow-up. I want to mention that there are other kinds of singularities besides shocks that are known in fluid mechanics. There's the breakthrough work of Merrill, Raphael, Ranyansky, and Schaftel on implosion singularities. So this was work in spherical symmetry, where the density and velocity blow up at the center of symmetry. Yeah, I see, Martin, I'm creeping up on time. Thanks for the reminder. So this is a much more severe singularity than a shock because the density and velocity blow up. And it's much less clear if you can hope to continue the solution, and if so, in what sense. I also want to mention that this framework has been applied in other situations in 1D where you have viscosity. So Owen Paspalatos understood the time of first blow-up for dispersive and dissipative perturbations of 1D burgers. So this is a relatively recent paper within the last year or so. And then very recently, so just a few days ago, Chaturvedi and Graham, they have recent progress on understanding the inviscid limit for 1D viscous burgers. So they study like you can think of it as a shock-forming burger solution, but then they add a small amount of viscosity and try to study what happens to the viscous solution as the viscosity goes to 0. And as far as I understand, they separate the solution into the viscous solution into the part that is worse than C1/2 and the part that's better than C1/2, and sort of understand a little bit about how the limit works in that case. I think this is a very nice result. Okay, so here's a picture of a regime where you have a strictly convex singular boundary. This is the regime that Elinak studied. This is the regime that is featured in the work of Buckmaster, Scholar, Vikol. Here, the lowest point on in this picture, where lowest should be thought of as relative to some Cartesian time function. The lowest point is supposed to be B star, and it's supposed to be the unique lowest point. What you're supposed to be seeing is convexity in all directions in this picture. And when you have that kind of convexity, then even though the details haven't been written down anywhere, it seems likely to me that you can sort of use Cartesian flat foliations to sort of ground wall from all possible directions to sort of implicitly access the entire singular boundary. However, if you do not have convexity, in some direction, for example, which is what happens in perturbations of plane symmetry, then then you need to do something more refined, which is what I'm doing with Leo. Then you need to then Cartesian flat foliations are not going to give you the full picture, and hence one needs foliations that are adapted to the precise shape of the singular. Okay, so let me just jump to the end of the talk, so I can leave a few minutes for questions. As I mentioned at the beginning, it would be great if someone could do this for the coupled problem, not just the fluid, but Einstein Euler. This would be a problem with multiple speeds of propagation, in which the fluid is the slowest speed. So you should think that gravitational waves are very fast, sound waves are very slow. If there's a shock, it kind of lives deep in the interior region on a surface that is viewed to be time-like by the space-time metric. And so that's a pretty difficult singularity. And it would be great if anyone can make any progress outside of symmetry. In symmetry, probably it can be done because you don't have to do energy estimates. The shock development problem, even though the restricted problem has been solved, the full problem of locally solving past the first singularity when there's vorticity and entropy, that remains open. But I believe Chris Adulu is working on that. Once this problem has been solved, of course, the next natural question is, what can one say about the long time behavior of solutions with shocks, at least in the perturbative regime? And now, at the very least, we have the result of Ginzburg and Rodniansky to inspire us that in principle, it might be possible to say something even for a fluid. And again, in 2D, incompressible fluids have global solutions. So maybe that's a place to start, but I should also caution that in 2 space dimensions, some of the aspects of the Ginzburg-Rodniansky work don't manifestly carry over because of the worst behavior of waves from the point of view of decay rates in 2 space dimensions. So I'm not trying to suggest that would be an easy problem by any means. And if you really want to make progress, you have to understand something about the long time behavior of the vorticity. And even in the incompressible case in 3DE, essentially nothing is known. So that tells you that the problem is possibly not going to be solved in our lifetime. And if you are interested in singularity formation, then just the singularity formation part, then besides fluids, there's lots of other systems that haven't been understood. Elasticity, crystal optics, nonlinear electromagnetism. The principal parts are much more complicated. They're not just like a Lorentzian metric anymore. You have these 4 indices that kind of wildly couple everything together. And the geometry of these systems has not even been well understood. Okay, so I'll stop there.
Let's thank Jared. All right, any questions for Jared? Jared, it looks like you were abundantly clear and everything.
Maybe I can make another attempt to make Sergio happy.
Sure.
Sergio, was my answer helpful to you about these initial data hypersurfaces for the rough time functions? Right. So I think the cleanest thing to say would be simply that this picture and these surfaces are cooked up for 2 reasons. First of all, so that these foliations are space-like. Second of all, so that they become
sorry, I was muted. Yeah, no, I still don't quite completely understand. So you have these barriers in a sense. Are they I didn't quite understand what they are used when you do the actual hyperbolic estimates. Are
Well,
they boundaries or what?
so
I'm
you
like,
have
in other words,
so I would like two things.
because you are
First of all,
estimating between two time-like.
I want these surfaces to be space-like just so I can do PDE energy estimates. Right? You don't want time-like. I mean, you could have null.
No, I
but you don't-
understand, but I'm talking about the time-like, these time-like things that you are constructing using these vector fields, these time-like vector fields. I don't understand what is a role
they actually they're
in
drawn
the
to be
estimates.
time-like. They don't actually have to be time-like.
Sorry?
They don't have to be time-like. They could be all you know for sure is that they're transversal to the space-like ones. So I drew them like they're time-like because they could be. It depends on the initial data. If their character doesn't really matter that much because the PDE
Right, but
the PDE that you're solving is
no, but what role do they actually play? What is the role they play in the estimates, in the hyperbolic estimates?
They don't
In the
play
energy estimates.
they don't play a role at all in the energy estimates. I don't do any energy estimates on these surfaces. Their purpose is to initialize the new time functions. I don't do any energy estimates on these surfaces. They're just how you construct the time functions.
Okay, yeah, no, so sorry.
These codimension 2 surfaces play an important role in the energy estimates, but not these time-like looking surfaces.
Hello?
Yeah, we can hear you.
Yeah, so no estimates are done on these time-like looking surfaces. Their purpose is to serve as surfaces of initial data for the time functions.
Okay, let's thank Jared again.